it's time to start looking at actual differentiation of functions of several variables. So, as with one variable calculus, differentiation is fundamentally about two issues: continuity and differentiability. Continuity means there are no breaks in the graph. We can see right away why this issue instantly becomes more complicated than one variable calculus. Because what is a break? In one dimension, it was easy. If it stops there and starts there, there's a break there. But in two dimensions, it's not so easy. Like, what if we have a surface that goes like this? Or what if we have our old friend, a torus? So this surface is z equals 1 over x squared plus y squared. So as x and y get closer and closer to 0, the denominator gets smaller and smaller. That means this gets bigger and bigger until at x and y equals 0, it's undefined. Now, the torus has a hole too, right? Doesn't it? What do you think? Is there anywhere on the surface of the torus where the tangent would be undefined? No. Is that important? Maybe. So what does continuous mean? These both have holes in some way, and yet they're not the same. So this is one of the important questions that we have to answer with multivariable calculus. And notice that we're already getting involved with concepts that are directly applicable to complex analysis and elliptic curves and Weierstrass equations, because remember, the Weierstrass equations are the lattice on the complex plane where all of the lattice points are poles. And right now, we don't know what that means. I mean, we can figure that it means they're undefined there, they go to infinity there, whatever. But now we're already starting to learn tools that will help us analyze and understand what's going on. And again, the Weierstrass equations and elliptic curves are, of course, central to the proof of Fermat's last theorem. So a differentiable function from R2 to R is one with a well-defined plane tangent to the graph at each point. So that means that there can't be any sharp folds or breaks. So in other words, it has to be smooth. So as with one variable calculus, differentiability is stronger than continuity. So in one-dimensional calculus, if we just have y equals the absolute value of x, oops, oh, I didn't hit that very well. This equation is continuous. It has a value for every value of x, but it's not differentiable because what's the slope right here? It's a sharp angle, right? So it's not differentiable. When we're looking at with several variables, there can't be any peaks or folds. So if we had a surface, we can't have anything like this. We can't have any points or peaks or folds, because at any of these spots, there's no way to define what the tangent slope is at this point, right? On this fold, it could be anywhere from this way to this way. So this function would not be differentiable at any of these places. So to determine whether the graph of a function of several variables is smooth, we need to define what it means to say that a function is differentiable at a certain point. So what does it mean to take the derivative of a real valued function of several variables? Well, when we took the derivative of a function of one variable, we were just looking at the slope, right? It was just the rise over the run, and then as this point got closer to this point, the slope would get closer and closer to the tangent point, the tangent line right here, and then the derivative at this point is just the slope of the tangent line. And there's something really important to notice about the slope of this line. It's a scalar, it's not a vector. It's not actually the direction of the change. It's only a numerical value that represents the ratio of how much y changes for each change in x. It's easy to confuse the tangent line of the graph of a function of one variable as a directional vector, because it seems to point in the direction of travel. But it's actually just a scalar. It's just the ratio of the change in y to the change in x. There is no actual direction in this value. So we need to do something similar with surfaces. So the derivative of a one variable function is the slope of the tangent line to this graph. So what is it in multiple dimensions? Let's say we had our old friend, the hyperbolic paraboloid. So what is the slope of this surface? Well, remember that if we're going along the y-axis, the slope is going downward. But if we look along the x-axis, the slope is going upward. So what does it mean to ask what's the derivative of this function? That's what we have to decide. So just by adding one more variable, we've made the question of what is the derivative of this function way more complicated. There are a few ways we could answer the question. Maybe we could specify the direction. So the derivative of this function is the slope of the surface along a particular direction. Or if we think that the derivative of a single variable function is the tangent line, maybe what we mean here is the tangent plane. So that up here, maybe it would be like a plane that goes this way and that way, so that the actual derivative is two-dimensional at each point. Maybe that's what we mean. Or I'll give you one more possibility. It's a little less obvious, but maybe we could look for the direction of greatest change. So the point is, there's no obvious answer here. All of these things are possibilities. Okay, but we have to figure out a way to get started. We need a way to get our foot in the door. What do we already know? Or what can we say about this surface? Well, if we want to know what the slope is on the surface, we need to know the direction. In one dimension, with a one-dimension function, you didn't need to know the direction because there was only one direction we could go. But now you need to know which direction you're going. So what are we going to do about that? It would be nice if we could somehow apply what we already know about differentiation of one dimension. Well, notice one more thing. I'm saying what is the slope in a particular direction, but those are two separate pieces of information, slope and direction, right? The slope itself is still a scalar value, but what that value is changes depending on the direction we're looking at. So what would be great is if we could specify a direction and then take the one-dimensional derivative along that direction. Well, if you think back to our examination of surfaces, we have already done that. That is exactly what we were doing when we set one variable to 0. We created a one-dimensional graph of a one-variable function. So for instance, the equation of this is z equals x squared minus y squared. And remember, in order to get the cross sections, if we just set y equals 0, then we get z equals x squared. That's just a parabola in the xz plane. In other words, that is a function of one dimension, right? It's a graph of a function of one dimension. It's the graph of x squared. So if we just set y to a constant, we can take the derivative of the resulting one variable function to get the slope of the surface in the x direction. And that is exactly what we mean by partial derivative. So now we can just begin to see how important vectors in linear algebra are to this topic. Because using just one variable calculus, what the partial derivative gives us is two pieces of information about a surface, two scalars, the slope of the surface in the x direction and the slope of the surface in the y direction, and of course more for higher dimensions. But the x direction and the y direction, that sounds an awful lot like standard basis vectors for R2, right? Without going more into it right now, just imagine if the partial derivatives with respect to x and y are coefficients of the standard basis vectors. Suddenly we have a whole lot of information to work with. That's exactly where we're headed. So if we know how to take the derivative of a function of one variable, then taking the partial derivative of a function of several variables is actually quite easy. To take the derivative, say, along the x-axis, all you do is treat the other variables as constant and then just take the derivative as though it was a one variable function. So if f of xy is a function of two variables, then the two partial derivatives are df over dx and df over dy. So this means this is the derivative of f in the direction of the x-axis. This is the derivative of f in the direction of the y-axis. And then if it's the variable of three functions, it's same thing. This symbol is called a del. It's just basically a d, but they curled it to distinguish it from the d. When we fix the value of one variable, we're converting this function into a function of one variable. So for example, if f of xy equals x squared y plus y cubed, and we fix the value of y to 2, then we basically made a function that's f of x comma 2 equals 2x squared plus 8, right? Because we just plugged in the y for 2, and then what we end up with is just a function of one variable. So if you think back over the last 3 or 4 videos, this is what we've been doing all along. In the last video where we were looking at the quadric surfaces, we were taking the slices along the x-axis and the y-axis. So like when we looked at the elliptic paraboloid, we took a cross-section this way, and we got this, and then we took a cross-section along here, and we got the one that went this way. And that's what we were doing. We were saying, let's say that y equals 0, and then what's left? This was the graph of that function. So we would set y equals 0, and then what we would be left with is just z equals x squared, which is a parabola in the xy plane. And by the same token, when we took the derivative of a curve, if we had that ct equals xt yt, then to take the derivative of this, we took the derivative of two one-variable functions. So we've been doing this all along. This is what you do. You hold everything constant except for one variable, and then you just take the derivative along that variable. So we'll do some examples now, and when we take the derivative of a function, it's not like this. We don't actually make y constant. We just think of it as constant when we're taking the derivative. So, for example, if we have that f of xy equals x squared y plus y cubed, let's find the partial derivative with respect to x and the partial derivative with respect to y. So to take the partial derivative with respect to x, we hold y constant, and then we just take the derivative as though y was constant. So it would just be 2xy plus 0. And to take the derivative with respect to y, we hold x constant, and we have x squared plus 3y squared, okay? So notice one other thing. Just like with one variable calculus, the derivative of a function is not a value, it's a function of x and y. At every value of x and y, the derivative at that point will be different, right? As we go out here, it's gonna get steeper, steeper, and so on. Okay, so to indicate that a partial derivative needs to be evaluated at a particular point, x0, y0, we can write it one of these ways. So we might use any of these depending on whatever feels best. We might also use some other notations. If z equals f of xy, then instead of df of dx, we could say dz of dx and dz of dy. And then also, instead of df dx, we might use a subscript like that, f sub x or f sub y. Or, of course, we could also use zx and zy. Now, when I first learned this notation, I found it confusing because it just isn't obvious to me from this. Is x the variable that we're holding constant, or is x the variable that we're allowing to change? And I think the way to think about it is, like, if f was a function of 3 variables, then when we take the partial derivative, we're taking it along one direction, which means we have to hold everything else constant. So this must be the one that we're deriving with respect to, and meaning that we have to hold the other two constant. So just remember that when you take the derivative with respect to x, it means you're asking how does the function change along x, meaning nothing else changes, only x. How is the value of the function changing from moment to moment as we move along x? Okay, so let's look at another example. If we have that z equals cosine xy plus x cosine y, let's find the partial derivatives of dz with respect to x at x0, y0, and also fy at a specific value. Okay, so how do we do this? Well, first thing we have to do is find the partial derivatives. So we do that just like we did in the last example. So to take the derivative of z with respect to x, we treat y as a constant and take the derivative of the rest of it. So what we have here is we're going to have to use the chain rule. So the derivative of cosine is minus sine times the derivative of what's inside, which in this case would just be y, because it's the constant, right? And then x goes down 1 degree. And then here, cosine of y is a constant. So it's just the derivative of x times a constant, so it's just cosine y. Now to take the derivative of this with respect to y, this time we hold x constant, and this is almost the same thing. So it's minus sine, but now x is constant, so you have to take the derivative of what's inside. So that's just x. And then this time, x is constant, so we take the derivative of cosine y, and we have minus x sine y. Okay, so these are our derivatives. So now let's just plug in x0 and y0 and see what we get. That's easy here. So d0, dz, dx at x0, y0 equals just y0. It's sort of pointlessly easy. We're just plugging in the specific values for the derivative. And then for this one, if we have fy at 2 pi over 2, we have to plug x and y in to this one. So we have minus 2, sine of 2 times pi is just pi, minus 2, sine of pi over 2. And so sine of pi is 0, so that's just 0. And then sine of pi over 2 is 1, so it's minus 2. Okay? So if we're taking the partial derivative of a function of more variables, it works the same way. So for example, if we had f of x1, x2, x3, x4 equals sine x1, x3 minus cosine x2, x4, and we want to find the derivative of f with respect to x3, what are we going to do? So we hold 1, 2, and 4 constant. Here we just use the chain rule. So this would be, the first part would be cosine x1, x3 times the derivative of what's inside, which is just x1. Now x2 and x4 are both constant, so that's just going to be 0 again. So that's the answer. Good. So we can interpret the partial derivative as the slope of a line tangent to the surface. So if we had a fixed point, x0, y0, so if we had a surface here, and then we had a point here that's x0, y0. So this is the y-axis, this is the x-axis. So if we take the planes that are parallel to the xz axis through this point, so it's like the plane that goes this way, then the intersection of this surface with this plane is just going to be a curve along this surface that's on a plane that's parallel to the xz axis. And if we took a plane parallel to the yz axis through the same point, we're going to get one that's the intersection of this surface with this plane that's going this way. So in both cases, we just end up with a one-dimensional curve. And these two curves intersect at the point x0, y0, f of x0, y0. Remember, this is what the graph is. We learned this when we were first discussing surfaces. Then this surface is the graph of this function. So at this point, it's x0, y0, and then f of x0, y0. And these two planes intersect at that point on the surface. Now, in the plane that's parallel to the xz axis, y equals y0 all along this plane, right? Y is always y0. So the equation of this curve in that plane then is just z equals f of x comma y0. We're holding y constant, and then as x varies, then z varies up and down, always along that plane. And then the slope tangent to this curve at that point, where x equals x0, is the derivative with respect to x of f of x comma y0 at x equals x0 equals. This is the derivative of a function of one variable, namely this curve, at the point x equals x0. That's the same as the partial derivative of f with respect to x at that point. So this is basically the partial derivative of fxy when we hold y constant. And then we end up with the partial derivative with respect to x at that point. That is the partial derivative of f with respect to x evaluated at the point x0, y0. And what we end up with, so what this is the tangent line to this curve in this direction. And then of course, if we go through the exact same thing, holding x constant, then the tangent line to the curve that's parallel to the yz axis is going to be df dy at that point. So to repeat, with respect to y means that you're holding everything else constant and the only thing changing is y back and forth. And then how does the function, the value of the function change as y moves back and forth, and everything else is held constant. That's how you get that curve. Okay. Now, in terms of limits, of course, we're talking about derivatives, so we have to be talking about limits. In terms of limits, the partial derivative of f with respect to x at the point x0, y0 can be written as the limit as h approaches 0 of f x0 plus h comma y0 minus f of x0, y0 over h. So what is this? This looks more complicated, but all it is, remember what's the derivative of a single variable? If we just had the df over dx, it's the limit as h approaches 0 of f of x plus h minus f of x over h, right? So the only difference here is that we've added this second variable, but it's being held constant. The only thing changing is h. Now, the partial derivative with respect to y is actually a little bit different. It is the limit as k approaches 0 of f of x0, y0 plus k minus f x0, y0 over k. So it's the same, but of course it's now we're getting closer to y in the y direction and x is remaining fixed. One important detail is that we're actually taking two different limits here. So you just have to keep that in mind. We can't actually write this simply as x0 plus h and y0 plus h minus x0, y0 for reasons that we'll get to soon. But when we're dealing with multiple dimensions, it's actually more complicated, and we have to be careful about how we're approaching the point. So just like one variable calculus, partial derivatives can be interpreted as rate of change, either in the x direction or the y direction. So if you imagine, for instance, a mountain like this, say with the ridge along the x-axis, the rate of change of the elevation of this mountain is different depending on which direction you're going. If you walk up the ridge, if you stay on the ridge and walk up, it's actually quite shallow. But then if you turned left 90 degrees and went down this way, the rate of change is actually quite steep, right? Okay, next time we will look at continuity and then we'll put it together. Thank you. I want to give a special thank you this week to my Patreon supporter, Patrick Collins, as well as Chiff1 and everyone listed here. These videos would not be possible without all of your generous support. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.